Okay, here we are, Unit 2 on filters, and we're in note set 5. We've got one more note set in this unit after this one, where we'll do something totally different. But this one is focused on two other ways of using various alternate structures to get some nice parametrically controlled forms for our filters. There are some readings here. I'll also allude to some other reading sources throughout the notes. So really this note set is split into two parts. The first part is this so-called regalia filter, and the second one is what's commonly known as the Chamberlain filter, although it should be known as the Collins filter, but we'll get to that. So the regalia gives a nice structure for doing shelf filters. And so we're going to start with our denormalized continuous time shelf filter, first order low shelf filter, and we'll do it for the boost case. So that's what we came up with before for the continuous time version of that. But we now know how to take something and break it down into high pass and low pass. That's just pure algebra. So nothing new there. We're just doing a little bit of algebra. And then now at this point, we go, oh, high pass I can implement with an all pass filter, and a low pass I can implement with an all pass filter. We saw how to do that in the previous set of notes. So we decompose each of those. Here's the high pass, and here's the low pass. And so each of those get decomposed in terms of an all pass filter. And I'm just defining these things right here. So we know that is the form of an all-pass filter. That is the form of an all-pass filter. In fact, it's the same all-pass filter. So we can now plug these things into these positions and see that we end up getting something that looks like this. And so we can see that we get our transfer function for our low shelving boost filter by just combining two parts, each one involving a all pass filter. Now, if we look at that, it looks like we need to build two different all pass filters, but it turns out that with a little bit of algebra, we can actually see how this just gets shared between the two different parts of this. And so before we see that, let's do the same thing for the cut case. So I've just flipped this upside down, and what I did here was a little bit different. Instead of putting the V0 in front, I reciprocated it. So this form is going to be, when you do the cut, you do put in a V0 less than 1. So remember, that's the non-dB value of the amount of attenuation that you want. So you start with a negative dB attenuation, convert it into a non-dB value, which will be a value less than 1, and you plug that in here. Now we do the same kind of thing. Decompose that. So we see that we have a high pass filter and a low pass filter, and we decompose each of those. And the only difference is that now we have this structure as those constant coefficients in the numerator and denominator. So the form is the same, but the values that go in for the coefficients are slightly different. So I called that A sub C. And it's the same thing. And again, we can write it out as a sum of two different parts. And we see that both of these look exactly the same. The only difference is what we put in there. So in other words, what we put in as the coefficients for those filters. And so it leads to a nice, simple, consistent structure for both cut and boost, which is nice. You may remember when we first talked about these, I said, how are we going to do that? How are we going to flip the transfer function to get the cut case? And I pondered, are we going to need two different circuits? Well, it turns out no. Now, before we look at how to build these, since this is a digital audio signal processing class, we're going to convert these to discrete time, and we're just going to do that using our method of bilinear transformation that we learned in a couple note sets ago. So we've got these. All we got to do is apply bilinear transform to each of those. That will convert all of these into discrete time, and that will convert those into equivalent discrete time. So there they are. Going from here down to here is literally just changing the S variable to the Z variable. But now what's important is we have to figure out what these coefficients are. And you'll notice that those two have the form of a discrete time all-pass filter. And for that matter, these had the form of a continuous time all-pass filter. Mirrored zeros, reciprocated zeros. And so now we just have to figure out how to make the A sub C for the cut case and how to make the A sub B for the boost case. And if you work through the application of the bilinear transform, just a little bit of algebra, you'll find out that they turn out to be these two things. So they look very similar. The only difference is what goes here. Everything else is the same. Now I say that there's one drawback here, and that's that this thing has to be computed in terms of both gain and cutoff, but that's not a huge drawback. And so if we look at this equation, we need, let's just look at, well, either one of these is fine, right? We're going to put this, right? This whole thing's going to multiply x of z. So x of z is going to go into that one. X of z is going to go into that one. Well, then we do two different things with that. So why not just make that one operation? And we can see that through some algebra here that we can group that. And what we end up getting is something that looks like this. So you should be able to convince yourself by tracking your way through this block diagram that it does indeed give what we had on the previous page as far as the equation goes. But the signal goes into one all-pass filter, and then it also goes here and here untouched. And then the output of the all-pass filter, let me get rid of some of that. The output of the all-pass filter is added to the input up here and subtracted to the input down there. So that's these two things, right? The plus and the minus. And then it gets multiplied by a half up here and V over 2 down here. Again, we can see that here, the half out in front and the V0 over 2 there. So you should be able to convince yourself that that once you add those two things together, that in fact does implement that. And so now to switch between cut or boost, we just have to change the two coefficients in there. Well, really just one, AC, but it shows up in, or AC or AB just shows up in two places in the transfer function. Now, we can come back here and we can do some algebra to get that into a slightly different form, but we can also just kind of trace our way through here, right? We've got the signal going through A of Z and then it goes to two places. Well, now the signal goes through A of Z and it goes to two places, and then those sums have the input. So the input comes here and it's added in one place and subtracted in another, and then multiplied and added together. So this thing looks like it's pretty clearly the same thing. And then the final one, if we just think about this, what's really happening here, we can think about the signal going through here, and then we get a X and the output of that. So that would be give us a 1 times V0 over 2 there, and a 1 plus V0 over 2 there. So a little harder to see going from here, but I think you can, if you spend a little bit of time, work your way through that. But you can also get there algebraically. Just come back here and try to manipulate that into a form that would be showing that. The advantage of this is there's no summations. We just run the signal through the filter and then we just multiply it by two things and then we add. So we get rid of the two adds. And so in some applications that might be an advantage, but really all three of these are pretty nice structures. And the beauty is you can very easily switch between cut and boost. And that's the advantage of this. So that's the regalia filter, and that's a pretty widely talked about filter in digital audio. The last thing, or the second part of this we want to talk about, is something that's widely known as Chamberlain's filter. And this comes from a book by Hal Chamberlain. The second edition came out in 1985, and I think the first edition came out in 1980. So that's a book called Musical Applications of Microprocessors. So oddly enough, a lot of the chapters in this book, just like I'm doing in this course, talking a lot about continuous time stuff and then how to transition it to discrete time. That's a lot of what went on in Chamberlain's book. So he has a lot of chapters in there that focus on continuous time stuff. And so because this book was pretty popular, the filter became known as Chamberlain's filter. And it's got some really nice properties. One thing is once we build it, we get 4 filters for 1. And that was very popular in the analog synthesizer world. So Moog synthesizers back in the 1960s and into the 70s were all analog before they made the digital synthesizers that are widely used today. But in a analog synthesizer, you wanted access to all these different types of filters. And this was a circuit that just by a switch could give you all 4 of the classic filters. But the really big thing about this is that complete perfect decoupling of the center frequency of your filter for band pass and band stop, or cutoff for high pass and low pass, and the Q. So you can have 2 knobs that independently adjust those things, and that's really nice. And I say that we can get the band stop. It's not really shown in this book. I can't remember if Chamberlain talked about it or not, but I'm going to show it to you here, at least to some degree. Now, it's called the state variable filter in this book. I can't remember if Chamberlain refers to it that way or not. It's been a long time since I've read that book. But it's not clear in the DAFX book where this filter came from. So he references Chamberlain's book, but he doesn't really talk about it. But he also doesn't talk about the pre-Chamberlain history of this filter, and it's really a pretty famous filter. Nor does Sulzer really address why he calls it, and many other people call it, the state variable filter. So I'm going to cover that here because it's nice to have that history. And if you go back to, I think it was the last note set in Unit 1, I talked about the state space view or the state variable view, just an alternate way besides transfer function or differential equations or frequency response or impulse response. It's just a new way to think about a system. So any given system can be a state space filter or system. It's not like this one is state space and that one is not. So to say that it's a state variable filter is a little bit of a misnomer, but that's how we get to it. We use state variable analysis to get to this filter. Then we implement it, and it's just a filter. It can be described by any of the other characteristics or models. So here's a little bit of history on this. There was a guy named Dennis Collin, and he worked for a company called ARP or ARP. And he was the one who did a lot of the designs of the early ARP synthesizers. So they were introduced, I think, in the late 1960s and very popular in the early 70s. They were a competitor to the Moog synthesizer. And you can see over here that I'm saying here's an early ARP 2002 synthesizer, and that was used in the mid 70s, late 70s to make the sounds of R2-D2 in the Star Wars movie. So has some history. So this filter, even though it was originally designed for the ARP 2500, would have also been available in the ARP 2002. Well, this is a picture of the 2002, and this is the 2600. So anyway, these kinds of filters are what make analog synthesizers able to make those crazy sounds like R2-D2. So that was 1971, and that paper is available at this link. I think that's still valid. You can see that whoever made this didn't know how to spell Dennis Collins' last name. But anyway, that's the deal. And then in 1980, and this is the second edition, 1985, Chamberlain wrote a book. We just were referencing that. And what he did in that book, even though it was talking about microprocessors, he talked about op-amp implementation, as did Dennis Collins, showed op-amp implementation of this, at least in principle. But Chamberlain, true to the title of the book, also talked about how to convert it to a discrete time version. And we're going to basically go down that path with a little bit more detail than might be available in the Chamberlain book. And then 1997, John DeToro, also a big name in digital audio. He has a series of papers. I just say effect design. I think this might have been, there were 3 parts, part 1, part 2, and part 3. I think there were 3 parts. I can't remember which part, but I am telling you which pages, so that should help you find it, should you want to find it. Well, so what did DeToro do? He didn't go from Collins' op-amp version to a discrete time version. He just directly derived the discrete time version of this filter. So 3 different historical touchstones for this filter. But like I said, a lot of people call this the Chamberlain filter because that's probably where most people learned about it. People were more likely to read a book than papers in Journal of Audio Engineering Society. All right, let's get into how this thing arises. So we're going to go back and remind you a little bit about continuous time state space or state variable representation. If you remember, the idea was to replace one nth order differential equation with n coupled first order differential equations. And the coupling is accomplished by writing it out in matrix and vector form. That's why this is sometimes called the state vector representation. So I've written it out here, and I've written out the vectors explicitly, but I've written out the matrices symbolically. So I use uppercase, bold, non-italic to represent matrices. And in the more general form, that would be a matrix, but we are limiting ourselves to a single input here. And so that input matrix becomes a vector. So that'll be a column vector. And I'm pointing out that I changed the notation just a little bit from what I had in the previous set of notes. I don't know why I used the Q notation there and I used the X notation here. Well, I do know why I used the X notation here. If you look in the literature for state space, it's almost always X is the state vector. So I don't know where I got the Q from, probably some book that I pulled off my bookshelf when I first made that note set. But here I'm resorting to the standard. So back in that earlier note set, X was our input. Well, so now we're using F. Although if you look in the state space literature, I think you'll see that U of T is a more common notation for the input, but I avoided that because I like to keep U of T for the unit step. We'll encounter the unit step in just a little bit. You should have seen the unit step U of T in your signals and systems course. So A is called the system matrix and B is the input matrix. So that's the system equation or the dynamics equation. And then we have the output equation, which maps the state vector. So we have n different states into m different outputs. So here we are going to allow multiple outputs. And what we'll do is, remember we said we wanted 4 different filters, low pass, high pass, band stop. Those 4 outputs, each one will correspond to the output of one of those 4 filters. And so now we have the output equation, and we're going to have 4 of these. Each one of those 4 outputs will correspond to the output of one of the 4 filter types that we're trying to get. Low pass, high pass, and band stop. So this C matrix will be M by N, so that it interacts with the n-dimensional vector to give us an m-dimensional output vector. And then D, since f of t is just a single input, D will be a column vector here, and that's called the feed-through matrix. So we're also going to limit ourselves to just the second order case, because we're looking for second order versions of these 4 filters. You could do higher order versions of this, but the classic filter that Dennis Collins developed and the Chamberlain and Totoro looked at were just second order, and we're going to have 4 outputs. So our system equation will boil down to this, and you'll notice that I'm using that special canonical form that we had from a previous note set. So if you're not clear why I'm doing it that way, go back and look there. So here's our state vector. We could write that as just x of t, and that x would be lowercase bold non-italic, and then we'd have x dot of t, and again that would be the x would be lowercase bold non-italic, to keep with our standard for vectors. But we won't really need that here, so we'll just stick with writing these things out explicitly, which is easiest and perhaps best when you're dealing with just a second order case. And then our output equation is going to boil down to something that looks like this. And it will turn out that we can eliminate the input. We would often, as we showed, well, right here, include the output, but we won't really need that. And in fact, we're going to pull a little trick at the end so that we don't really need that. So one of our outputs, the high pass output, is going to be found not exactly following that rule, but we'll see when we get there. So that's an interesting point. We can follow the theory to a point, and then when you get to the implementation, you can kind of go, yeah, but it might be simpler to just grab that thing over here. So that's what we'll do in this case. So let's rewrite this system equation to just try to understand what it is that we've got going here in this classical canonical form. So we can see here that we're just writing x1 of t is going to be equal to x2 of t, or I'm sorry, x1 dot of t is just equal to x1 times 0 and x2 times 1. And then we can also see that x2 dot of t is going to be equal to minus a1 times x1 plus minus a2 times x2 plus f of t. So we write those 2 equations right there. So those are just writing out explicitly the system equation or the dynamics equation for the state form, the state variable form. And now we're going to convert this into Laplace because we're trying to understand how to pick those A1s and A2s to give us the filters that we want, low pass, high pass, and so forth. And so what we can do is remember that a derivative corresponds in Laplace world to multiplying by an S. And we are, since we're striving to find a transfer function here, we're assuming initial conditions are 0, because that's the condition under which the transfer function is defined. So it's not like we're making that an assumption. It is just part of the definition of finding the transfer function. Otherwise, we'd have some additional terms here that included the initial conditions. And when we're finding a transfer function, there is no role for those. So we leave those out by definition. And so this goes to this side and this goes to this side. And then I do the same thing down here, except I didn't switch things around. So that gives us the S times that, and then just the Laplace functional forms for those things. So now we've got our system equation written in the Laplace domain. And so now I can just solve this. I'm going to solve for x1 by dividing by s over there. And I'm going to solve for x2 by dividing by s over here. And so now I have forms that tell me what x1 and x2 are. Well, but there's also an x2 over there. But let's not worry about that yet. But we'll see how we can get all of this. So if we just look at this from a block diagram point of view, remember we said way back in that original note set on state space, we said, oh, a good choice, not the only choice, but a good choice for state variables are the outputs of the integrator boxes, 1 over s's. And so here's where we've put our state variables. We're just writing them in the S domain notation. That's all. And 1 over s corresponds to differentiation or integration, because s corresponds to differentiation, right? Remember that day in Calc 1 when you'd been learning about derivatives, and then they said, okay, now we're going to talk about the antiderivative, and it turned out to be the integrator or integration. So integration and differentiation, part of the calculus, fundamental theorem of calculus, tells us that they're linked like that in kind of a reversible way. So if I have x1 here from this relationship, that means that x2 has to be divided by s to give me x1. And if I want x2 here, that means that I need all of this stuff. All of this stuff needs to be in front of the 1 over s so that it will give me the x2. So there's a form for this system, but the question is, how do I get all of this stuff there? Well, look, this is coming from the input, and these two things are available right there. So let's connect all that together. So I take the f of s coming in as the input, and then I take x2 and x1, I multiply them by the appropriate coefficients, and I put the negative signs. Add all those together, and that gives me this thing shows up right here, which then gets hit by the 1 over s to give me the x2. Great. There's a block diagram that describes the dynamics of this filter. I still haven't necessarily set that it is a high pass and low pass and band stop. That will depend on the particular values that we have there and how we combine the states to give outputs. So that's the part that we need to work towards. But we've seen how we can go from a state variable view to a nice block diagram view. Now, I suppose we could have just started there and not called this a state variable filter, but people call it a state variable filter. So I wanted to show you why. How did we get there from the state variable idea? And then here's our output structure. We're going to take the two states, and each output consists of a linear combination of those. But as I said, we're going to cheat. We'll cheat a little bit when we get a little bit farther into this. So in principle, every possible output would just be some appropriate choice of two coefficients that would meld those two things together. But we'll see that for at least one of the filters, we can cheat a little bit. Okay, so how do we get the filters that we want? Remember, we want second order filters, and I'm showing the high pass, the band pass, and the low pass. I'm not showing the band stop. We'll throw that in later, but these are the three most characteristic filters. And I've put them in a particular order. First, notice that the denominator is the same in every one of these. The only thing that's different is the numerator. And the big difference is the power. So we've got an S squared. We saw that a couple note sets back when we first talked about continuous time filters. We said, oh, an S squared for a second order filter, an S squared in the numerator gives a high pass, and an S gives a band pass, and a constant gives a low pass. And then why is that there? Well, remember we saw that it had to be equal to that, so that when we go to low frequencies, these terms go away and our gain is 1. And then we saw similar kinds of reasons for why we needed that. And likewise here, when we go to high frequencies, these two terms are negligible, and that goes to 1. And so that's why we need no coefficient in front of that one. So, but the important thing is this descending S squared to S1 to S to the 0. And remember, our integration boxes, if we had an S squared, would knock that down to an S, and the next integration box would knock that down to a constant. So that's the key. So suppose somehow we built this high pass filter. Let's not worry about how we're going to get it yet. We'll see that in just a minute. But suppose we built that, then all we need to do to get so we have the high pass out. To get the band pass out, we just run it through a 1 over S. And to get the low pass out, we run that through a 1 over S. Now, yes, I should have some coefficients here. So I might have to have a constant here and a constant there. But that's just a scaling issue, setting the gain. So that's not the nature of the filter. So that's the idea. If I can build the high pass, I get the other two for free. And I should also point out, remember, here's where we get the band stop. The band stop we saw back in a couple note sets ago, that the numerator was S squared minus omega C squared. Remember, that put zeros, conjugate zeros, right on the J omega axis. So boom, taking the response down to 0 at some particular frequency. That's what made it a band stop. But if we see that S squared comes from here and the omega C comes from there, omega C squared. So if we took this and subtracted that from it, we'd get that. So all we have to do is take the output of the high pass and the output of the low pass and subtract the low pass output from the high pass output, and we have the output for the band stop. So we can add that to our diagram. And again, we'd have to have, like I said, the right coefficient. So we would need a coefficient here, and we'd need a coefficient here. But again, I'm not worrying about those coefficients. Okay, so we have this general idea now. The question is, how do we get the high pass? Well, let's look at this. Here's our canonical state space form that we just came up with. Again, it's not really state space. We just got to it from state space. Once we get there, once we get here from state space, we can forget about the state space. But everybody calls this the state space filter, so I wanted to take you through that. So let's look at this. We need to verify that if we build this kind of thing with the proper choices of these, that we can make this be the high pass output. If we can, then there's the high pass output. It gets integrated to give the band pass, and that gets integrated to give the low pass. And I just didn't show the band stop on here because it would make it messy. So what is here? Well, it's f of s, and then it's minus a2 times 1 over s times the high pass, and it's minus a1 times 1 over s squared. That's where that comes from, times the high pass. So now I've got something here that is in terms of high pass, Laplace transform, output transform, and the input. So I can group things together, multiply by s squared on both sides to clear those out, And now I'm going to group these things together and factor that out. And I end up getting something that looks like that. And now I bring this and this together. So I take the FS and divide it over on the other side, and take this and divide it over there. And there it is. And wham, there is my high pass filter structure. Well, okay, it's not technically high pass until I set these to the right values that we saw in our study of classical second order filters. And there we saw that A1 had to be set to omega c squared, and A2 was set to omega c over Q. And remember, Q was that quality factor. The larger it gets, the closer the poles are to the J omega axis, and the higher any peaks are in the filter, whether it's a resonant low pass or high pass, which is the case here, or a band pass filter. The bandwidth gets very narrow relative to the center frequency. But that's the idea. So now we have the whole structure worked out here. Again, we got there starting at state space, but now we just have a transfer function. And so there it is in its completeness. I'm not showing the band stop here, but we could get it. Yeah, so that's everything there is. Now, we still need to put some coefficients here to get the right the right outputs. Okay, so but that's handled by our output equation, so we'll worry about that later. Now, here's the cool thing: we can get all four of these filters because, as we saw, all four of them have the same denominator. That means they have the same poles, and it's the state system equation or the dynamics equation that sets the poles, and it's the output expression that sets zeros and so forth. And that's what we're seeing. Although there are some fundamental zeros happening, as we saw, we get different numerators depending on where we tap off. But in the state equation, there's no tapping off. It's just how the states are related to the input. So the key thing is we get the four classic filters because all four have the same denominators, and we just have to pick out the right state combinations to make the things that we want. And this works because we've made this part here have the right S squared denominator or numerator, which then gets integrated once and then again to make the other two outputs. So that's the key. So each one of these stages, here's one stage, here's another stage, reduces the numerator power and gives us that decreasing power on S. And then we saw that we could combine two of the outputs to get the band stop output. So everything's really nice. But now we're going to talk about implementing this. So we need to build an integrator. So how do we do that? How do we build an electronic circuit that's going to give an output that's the integral of the input, a running integral? So that would be something that has a transfer function that's proportional to 1 over S. So if I put a capacitor impedance divided by a resistor impedance, well, remember, that's coming from the transfer function or the gain formula for an op-amp, right? The feedback impedance divided by the input or the input side impedance with a negative sign out in front. So that negative sign is not going to bother me. So once I do a little bit of algebra, I get something that looks like that. And that is an integrator. And that would be a circuit that looks like this. So to go from math to circuit, the more you know about how circuits give particularly standard results, the better you can say, here's the math and here's the circuit that's going to give it to me. So here's the impedance of the capacitor divided by the impedance of the resistor. This is our classic inverting op-amp. That's why we have the negative sign out in front. We'll have to keep track of that as we go through this, but it will all work out okay, because what we really have is a negative integrator, not an integrator. One little comment in passing, this works for ideal op-amps, but real op-amps have some voltage offset at the inputs, and so that small DC offset will end up getting integrated by this capacitor, and it will grow without bound. So that's one way to look at it. Or another way to look at it is, at DC, the impedance of the capacitor is infinite. So any DC voltage showing up either here or here, non-zero DC voltage, showing up in either of those two places, will end up having an infinite gain applied to it, and that will drive the output to the rail voltages, either positive or negative, depending on the sign of that DC offset at the input. So it's common to put some resistor around here and to make the value of that resistor fairly large. So like maybe 1 meg or 10 meg or something like that. So in actual implementations, you might see something that has a resistor in parallel with a capacitor, and they'll still claim that it's an integrator. So basically, you want to make the cutoff frequency of that. It ends up being like a high-pass filter, but you I'm sorry, a low-pass filter. You want to make the cutoff frequency of that below the lowest frequency that your audio would have. So that's just a word in passing. So we're not going to worry about that. So we need an integrator, and then we also need ways to sum voltages together. So here's a classic circuit from electronics for a summer, and we're summing two things together here, and then we that end up with negative signs, and then we have a positive here. Remember, we had in our summation, the input comes in without or with a positive sign, and the two feedback things come in with negative signs. So that's why these are going into the negative terminal. Now we can figure this out through superposition. So if we ground this and we ground this, we can see that the gain from here to here is going to be minus R over R, which is -1. Now you might be saying, wait, why doesn't this do a voltage divider so that you get a half of R? Well, with this grounded, there's no current flowing here, so there's no current through those resistors. So this is actually effectively at ground, and this then is effectively at ground. So if I ground this and this is grounded, this resistor is out of the picture. So when I first looked at this a long time ago, that bothered me, and then I figured that out. Well, I read about it in a book, I'm sure. And then this one, we've got a voltage divider there that sets up this structure, and then it gets hit by the non-inverting gain. But in that case, now we're going to ground this, so these two resistors now show up in parallel. So that's why we get this structure. So anyway, we can pick things, we can pick R3 to set this beta, and we'll be using that for setting some of the parameters of this filter, as we'll see. So now if we put all of this together, it works out like this. And this, it turns out we don't even really need any things here, any coefficients. And we get something that looks like that. Here's the summer, integrator. Remember, in practice, you might want to put a resistor around there. And it turns out that if we work all this out, the cutoff frequency is just 1 over RFC. So it's the same C here and here. Probably want to watch your tolerances there. And we have the same RF here. So if we wanted to make this adjustable, we would need a potentiometer that has two ganged potentiometers together. So that's one drawback to this circuit as an analog circuit. The other thing, this RQ here, that's part of that voltage divider going into the positive terminal of the summer. That's going to feed back this part here. And now you might say, oh, why is this one going into the positive? Well, remember, we have to account for the negative gain, the negative gain, and the negative gain. So there's a little bit of work that I skipped to get to this particular structure, but I've showed you enough. And this is being referenced in Zulzer's book as dating back to 1980, Chamberlain's book back in 1980. So two resistors control decoupled control of the cutoff frequency, or omega sub c, cutoff or center, and the Q. It's a beautiful setup. And you might wonder, we're just cascading these. Isn't that a problem? Well, that's the beauty of op amps. When we see something mathematical here cascaded, we say one stage has no loading effect on the previous stage. But in real circuits, that can be a problem. But op amps are famous for having low output impedance and large input impedance. So they isolate each other. So each stage should have minimal, negligible impact on previous stages. And then here's the big thing. We get this nice decoupled control. Two resistors. Or in the old synthesizers, they actually used voltage-controlled resistors here, so that you could use a voltage from someplace else, like an oscillator that would wiggle the Q around or wiggle the cutoff frequency around. That's how they get all those crazy R2D2 sounds. And you can also get the band stop here, but it's not quite going to be exactly as we had said earlier, because we now have to account for all the negation as we go through each stage. And if you care about that, you can either find it somewhere or you can work it out yourself. Now we need to convert this to discrete time. So we've got a couple options here, a few options actually. So we could just start over and say, ignore all that and just derive this kind of thing from a discrete time state variable approach. And that's what John DeToro did in 1997. And you can find that paper and track it down and read it if you want to do that. We could also say, hey, we've got a continuous time filter. Let's just do what we've been doing. Use the bilinear transform. Yeah, the problem with that is that it might not retain all that nice characteristics of decoupled control and 4 separate outputs and things like that. So it's a little bit of a risk doing that. I've not done it, but my guess is that since nobody else has done it, my guess is that, or at least published it, my guess is that it doesn't work. The third option, and this is what we're going to do, you can tell it's in big, bold red letters. We're going to say, well, I've got continuous time integrators. Let's see if we can come up with a discrete time thing that approximates an integration. And if we can do that, we should be able to just plug those right in and everything should carry over nicely. And so let's find a discrete time integrator. My claim is that this works like a discrete time version of integration. So let's take a look. From this block diagram, we can easily write the difference equation, right? We've got y of n, so what's stored here is y of n minus 1. So the output is going to be that y of n minus 1 plus x of n. So there's the difference equation for this. So now let's put in a impulse response. So if it really is an integrator, if you integrate a delta function in continuous time, you get a unit step. That might have been something you learned in a signals and systems class. If not, you can find that online. But it's pretty obvious. The area of a unit step is 1, and you're integrating along time. So you've got 0, 0, 0, 0. Then you hit the delta function. Boom, your integration value jumps up to the area of the delta function. And then there's nothing more added to the integration after that because the delta function goes back to 0. So the impulse response of an integrator is u of t. So we want our discrete time version to be the same. And my claim is that the impulse response of this discrete time circuit is the discrete time unit step. And so we can easily verify that, right? You've got to start off with this stored 0, put in 0, 0, 0, 0. The output just stays 0, right? We're feeding back a 0, putting in a 0, we get 0. 0, 0, 0. And then suddenly we've got a 0 stored here and we've got a 1 coming in here. So now our output becomes 1 at that point. So now the next thing that gets stored, we've got a 1 stored here and we're back to 0. So out comes 1. And so the 1 is stored again and 0 again and 1. So yes, that makes sense. The unit step is the impulse response of this circuit or this discrete time filter. So we do have something that looks like it's a discrete time version of integration. Another way to now see what's happening, since it's the impulse response is unit step, we can see that it does in fact do integration. So here's another way to verify that this thing looks like an integrator. Now that we know that the impulse response is the unit step, we're going to convolve that. And again, you learned convolution in signals and systems. Flip the unit step, slide it through the signal, and at each value of n, your output is just the running sum. And that looks an awful lot like an integration. We need to include the 1 over TS, which is the sample spacing. So that's TS is 1 over FS. But yes, this thing looks like an integrator. So we should be able to replace this, plug that into where we had the integrals or the integrators in our continuous time. So instead of going to the op-amp circuit, we'll go back to our basic block diagram here. And so here's the integrator. And here's an integrator, so we're going to plug in 2 of those discrete time ones. So 1 goes in here and 1 goes in here. And now everything else is converted to a discrete time. So I really should have, I was using X on the previous slide. We've been talking about F as the input. Sorry about that. Our input is now, F of n. And our output at some point is, Y sub 1 of n. Because these are all discrete time now. So that's what we have. But here's a problem. There's a problem with this, and it's called delay-free loops. So what is a delay-free loop? It's any loop where you can trace through the circuit, starting at one place and ending up back where you started, and never hit a delay. So let's start here. We can go through here. We can go down here, and we can go up here, and we're back. Did I hit any delays? Nope. What if I start here and I go all the way here, all the way around? No delays. So that's 2 delay-free loops. What's the problem with that? Well, here's the problem. So at some point, I need to compute y of n. What do I need to compute that? Well, I need z of n, right? Because that z of n is going to flow through here. It's going to flow through here. So to compute this number, I need z of n. And to compute this number, I need z of n. But to compute z of n, I need y of n. So this is really like a dog chasing its tail. And the same thing happens with this inner delay-free loop as well. So that's a problem. So here's how it's shown in Zulzer's DAFX book. what he says is, well, here's one of the loops right here. He just inserts a delay. And here's one of the loops where it was delay free before. And he just inserts a delay. And he's put in a few multipliers. I left those out in the previous block diagram, but those need to be there to make the right filter coefficients. So that looks like it works, except now you've got 4 memory locations. And it looks like this might be a 4th order filter because there's 4 delays, 4 memory locations. But if you look at this carefully, you'll see, you know what, this point here is just the delay of that. And this point here is the delay of that, but those are the same things. So these 2 points are the same. Likewise, this point and this point are the same. So why do this? Get rid of that and just tap this off here. And get rid of this and just tap this off here. So that's the idea. And so here it is redrawn, just a little bit nicer. And so that is a legitimate discrete time implementation of Chamberlain's filter. And this F1 value here, you want a certain FC. You have to put in your sampling rate, run it through this sign to get this F1 value. You want a specific Q, you take its reciprocal, and that's what goes in here. So this is very similar, aside from the sign, which just comes from, no surprise, that kind of thing when we convert from continuous time to discrete time. Kind of like a bilinear transform-ish kind of thing. So now we have it. So that's one form. Here's another way to fix it. And this diagram here is from DeToro's paper. So that's how he did it. And remember, he derived this directly. So he may have just come up with this directly. I can't remember. But it's also what was shown in Chamberlain's book. So Sulzer chose a slightly different form than what was in Chamberlain's book. Chamberlain's book matches DeToro's paper exactly. But nonetheless, and the symbology is a little different. We had F1 and Q1, and now we've got FC and QC, but they're exactly the same formula. So I'm just sticking with the original notations in each book. But now we get this as our transfer function for the low pass. If we compare that to the low pass transfer function for the DAFX version, you work that out, you end up getting something that looks like this. And if you plug in the right things here and match them up, you can compare these two things. And so what we'd see is that there's a delay by one sample there, but there's no delay here. And you can see that the R squared is just F1 squared, and that's the same as FC squared. So everything else is the same, just off by a delay. And so here I'm just comparing the two implementations to see how they differ. So the denominator ends up being exactly the same. The only difference is notational, FC versus F1, QC versus Q1, but those are the same thing. So the denominator is the same, so it's not messing with the dynamics. That's good. And then if we figure out the transfer functions, we have a z to the minus 1, and we don't. So the two versions are off by a delay on the low pass. They're off by a delay on the band pass, but they're exactly the same on the high pass. And so what that tells you is how to get the band stop from each of these two is going to be slightly different. And it doesn't really matter that our high pass is coming out, or our low pass and our band pass is coming out with a one sample delay. That's not a big deal. So either of these forms work perfectly fine. I don't think there's any real reason why you might want to use one or the other. Now, all three of these transfer functions are given in the DAFX book. If you go to DeToro's paper, I think he only shows the low pass, and so I worked out the other two on my own. So I'll leave it to you, if you want the band stop, to figure out how to get it in either of the two forms that you end up using. All right, one last note, or one last slide here in this note set. We've got a filter that has poles, and so we need those poles to be inside the unit circle so that our filter is stable. So it doesn't matter which of the two implementations you use, they both have the same denominator, so we can analyze that. I've just used the F sub C and the Q sub C notation here. What we want to do is factor that, and if we factor that, if we write out two factors here, we can multiply it out to give that form, and now we can compare this term to this, and this term to this. And remember, what we need is the R. This is our pole locations in polar form. So R is a non-negative number, but it has to be less than 1, strictly less than 1 for stability. So that allows us a simple way to analyze this. And so one way we can check is by just using this relationship here. We can see that if we need R less than 1, that means that we need R squared less than 1. That comes from here. And so that means that this quantity must be strictly less than 1. And then that inequality leads to something that looks like this. So that puts some limits on the interplay between this FC and this QC value. So remember, neither of these are the actual physical parameters that we're interested in. They're not little FC and they're not the Q value. But it does give us a way of analyzing and determining what range we're allowed to set those things. Now, DeToro did a little analysis, and he said, well, we rarely run the cutoff up very high. So we might limit the cutoff frequency to be like 1/3 of the maximum frequency that we're sampling at, right? So, or FS over 2. So FS is like 22-ish. Let's just say 21. And so 1/3 of that is 7 kilohertz. So like around, if we limit our FC to be 7 kilohertz or lower, 7 kilohertz for a cutoff frequency, whether it's low pass, band pass, or that's pretty high. So that's not an unreasonable limitation. And then he ended up with a nice analysis that said, under this constraint, all we need to do is make sure that both big FC and big QC are less than or equal to 1. So that's a nice way to check it. So you'd put some checks in your code, or you would limit the range that a user is allowed to set things. So just a nice little ability to set the stability. All right, so there's two famous filters, the Regalia filters and the Chamberlain filter, or the state variable filter. The second one is much more famous, I think, than the first one. And it's not always referred to as the Chamberlain filter. If you look in the world of analog synthesizers, you'll see lots of descriptions of the state variable filter. But it's useful in a lot of different musical applications than just synthesizers. So anyway, we got one more note set in the filter unit where we'll talk about something called comb filters. And those are going to be very useful later when we talk about reverb. Hope to see you there.